last time we had been talking about dimensional analysis, and so what I wanted to do today is maybe finish off a couple of components related to dimensional analysis, because when we start looking at pipe flow, the essentials of pipe flows are, of course, to be able to figure out how fluid flows in pipes, which might be pipelines or it might be industrial piping within a building. The critical issues that we deal with are to understand how much power you have to apply, for instance, to get natural gas from Pennsylvania to New York City. We deal with relatively simple systems. We're dealing with incompressible fluids in this class, but you could imagine, no doubt, that in moving real gas around, they're compressible. And so the equations that we'll develop for pipe flow, we'll find out, are basically Bernoulli's equation with the head loss term. And what we need is some kind of expression to represent the head loss. And we can develop that in a number of ways, and we'll try and do that. One of those ways, of course, is dimensional analysis. But just to recap what we had talked about, maybe with dimensional analysis, and skip back a little bit. So it's actually one of the most powerful techniques that we'll end up using. And so just to reiterate the few points that we have, so pipe flow, but also dimensional analysis. And so you'll remember that we talked last time about three requirements for dimensional analysis. And those were, I guess I won't abbreviate analysis. So those were geometric similitude, kinematic similitude, and third was dynamic similitude. And so you'll remember that the requirements for geometric similitude was that if it's a shrunk down model, all the dimensions have to be the same. So the ratios of lengths in our system have to be the same between the model and the prototype. And length over diameter is something that we'll use in pipes. Length of pipe versus diameter of pipe. So kinematic similitude was basically that we wanted the flow patterns around the pipe or around the airfoil or in the pipe to be the same. And the simple illustration of that was this diagram that was early on in your stuff. This flow patterns, this kind of streak diagram of flow around a cylinder, which was this. And that is that if we go at faster flows, at very low flows, we've said that the flow pattern around here will look like this form-hugging contour with a stagnation point at the front and a separation point at the back. As you increase the velocities to larger ones, you'll get this regime where you have these eddies which are shed off. I'm not sure which ways these would be circulating. You can see an eddy there, and you can see an eddy there. And so at any particular flow regime, which is indexed by a certain number, it would look different from the flow regime at a different velocity. And the index that we use to do that, to identify typically kinematic similitude, in other words, the kinematics of flow, the geometry or topology, morphology of flow is the same, is typically the Reynolds number. And so that's the second thing that we look for. And so we look for the fact that we have kinematic similitude, which is typically the Reynolds number of the model is equal to the Reynolds number of the prototype. And finally, if we satisfied both of these, then the big ask is that we want then for some other condition to be similar. And so that's our calculation. So if we know what the Reynolds numbers are, or we can have a diagram for the Reynolds numbers, then the other parameter we might want to judge behavior against would be the Euler number, which is what we've used so far for kind of open flows to get pressures acting on structures, or if it was a ship with a free surface, the Froude number. So Euler number for the model equals Euler for the prototype, or the Froude number for the model is equal to the Froude number for the prototype, depending on the deal. And that's really what the deal is. If, for instance, there was one geometry in it, then we might be able to do experiments on the model at this flow velocity, and this flow velocity, and this flow velocity, in terms of Reynolds numbers. We could measure the forces on the structures, and we get these Euler numbers. If you remember, just for our memory, Reynolds number is equal to a velocity, a density, and a length, characteristic length, over viscosity. It's actually equal to the viscous forces. Sorry, no. Can that? It's the ratio of the inertial forces to the viscous forces. And Euler number was what? It was a measured pressure, say, on our wing versus the density of the fluid and the velocity squared. And the Euler number is related to a pressure force divided by inertial force, as we'll see in a second. And so the idea was that if you can make these measurements on a model to get this relationship, maybe for some particular geometry we had, and we used length as the web of a wing and d as the span per se, then you'd have a relationship so that if you now use it for your true wing on your real plane, then you can go in an appropriate Reynolds number. If the geometry is the same, then you can find out what the magnitude of the appropriate pressure force that you'd have on it. It's nothing more than that. And so the beauty of this was that if we could just guess or have some intuition as to what the properties were that would affect the performance of our system, density of the fluid, viscosity of the fluid, the geometry of the wing, the pressures acting on it, the speed the fluid is flowing past it, and we could come up with some relationships just by experimentation, by using the so-called dimensional analysis, which is really dimensionless analysis, because all these parameters have no dimensions, and we could come up with some design values. So it's an incredibly powerful method, which will also apply to pipe flow. And so we thought about it in those veins. So it's really just a skill, an art, if you like, that allows you maybe to do the minimum, to do two things. One, it allows you to think about experiments, so you do the minimum number of experiments, so you don't need to do another experiment with a different viscosity fluid and a different velocity that would give you this point, because you'd expect it, if it has the same Reynolds number, you're wasting your time. You get exactly the same result in terms of pressure. So it allows you to choose what experiments to do on your model to maximize your yield for it. And it also allows you to make this switch from model scale to field scale in a, model scale to prototype scale in a rational way. So that's really what dimensional quote analysis is, which is really dimensionless analysis. So that's what or that's the big picture summary, if you like, of what we've done, and nothing else is important to do that. We could get those dimensionless groups by using Buckingham pi theorem, which is just a formal way of being able to get those magnitudes. But you could also guess them. And the reason that you could guess them is because we've talked about what we think the main ones are going to be. For kinematic similitude, we want to make sure the Reynolds numbers are the same between model and prototype. And to be able to say something about the system, then typically these other two dimensionless numbers are the other two groupings that will drop out. So it might seem like black magic or voodoo stuff, but it's actually a very well-established method of being able to solve problems. So this kind of puts together the things we talked about. Geometric similitude, the scale model has to look at a scale model. It can't look like a distorted model, otherwise you won't get the right results. Kinematic similitude, the Reynolds number in the model and the Reynolds number in the prototype have to be the same. And if you meet those conditions, then you can use the other properties, Froude number, Euler number, to be able to look at the pressures or shear stresses that are developed on a structure in the model and be able to translate those by scaling in the prototype. So that's it. You can do more complicated things that are non-steady state. We won't really worry about those. I think it's beyond this class, so we won't worry about that stuff. But the other thing that we can think about is that exactly what those numbers, non-dimensional numbers, might be. So what we've done is we've used Buckingham Pi theorem to be able to calculate what those dimensionless groups would be. It turns out that if you define different dependent variables, so in other words, change in pressure is equal to viscosity, density, velocity, etc. If instead you write that as velocity is equal to change in pressure, density, viscosity, you'll get apparently different groups. But you can always make them into the other groups by using that you got from the other dependent variables by switching things around. So they're not unique in some regards. So the reason I mention that is there'll typically be an exam question on Buckingham Pi. So you'd be told which parameters to use as your primary variable and which to use as your dependent variables, because it's just a grading issue that you'd come out with a very specific result if you did that, and you'd come out with a different result if you weren't asked to do that. And so Buckingham Pi is one way in which you can get these non-dimensional variables. The other thing you can also do is you can get them by looking at ratios of different quantities. And so you can think about the forces that might act in a flow field, and you could think about inertial forces, gravity forces, viscous forces. Inertial forces, of course, are Newton's second law, mass times acceleration, and mass would be density times volume times acceleration. Gravity force would just be the weight of something multiplied by gravitational acceleration, etc. Viscosity would be Newton's law of viscosity. This Newton guy gets around. And what you could do, if you could define, and pressure would just be, pressure force would be a pressure applied over an area. And so what you could do is you could take these kind of nascent small equations and look at every combination and permutation of the ratios of these two forces. And we kind of alluded to that in what we just said, in that if, for instance, you take the values for the inertial force and the viscous force, these two, I guess I could probably I can just about get them on the same screen. And you look at the ratio of those two, in terms of us defining them here, you end up with Reynolds number. And so these non-dimensional numbers we end up with that we call certain things after their originators are just the ratios of different forces. So the Reynolds number is the ratio of the inertial forces times the viscous forces. So in other words, inertial force is the force you have to apply to speed up flow within a flow, maybe around a dam or a weir. And the viscous force is acting against it. This one that we've used many times, right? This analog always acts against it. Friction acts against it. It's just really friction in the fluid, which is dissipating energy. If you look at the ratio of inertial forces and the gravity forces, it's just off here, but I'll make it smaller so you can get both of them on there, and look at those, then you end up with this Froude number, which is not so useful to us so far. And the one that's been important to us has been the ratio of the pressures applied on a structure, maybe by killing velocities, like on the nose of a submarine as it goes through the sea, to the inertial forces, come out to be these. So Reynolds number, Froude number, and Euler number in terms of those. So those are typically the most important ones that pervade this class. Jumping ahead, and we'll come back. So when we talk about pipe flow, we'll talk about flow, just think about this. We'll talk about flow in a pipe. And of course, flow in a pipe could occur in two ways. One is where the complete cross-section of the pipe is filled with fluid, and you apply pressure upstream to get it downstream, like you normally think of pipes. Or a pipe that perhaps is half filled with water, in which you can't really apply a pressure upstream to downstream to move the fluid, because the fluid will flow the easiest path, which is just through the low viscosity, low density air on the top. And so pipe flow is true in both of these cases, but the property that will govern pipe flow in this case would be we'd want to get Reynolds number similitude, but we'd measure the behavior of this in terms of the Euler number. And in the half section filled pipe, we'd expect to get Reynolds number similitude, but actually it would be the Froude number which would control behavior. This free surface flow, where the flow in this pipe is really just happens to be in a pipe, but it could be an open channel, and all the flow is just being driven by gravity. Higher elevation, lower elevation, and all the flow velocity related to that. And so for those circumstances, those three non-dimensional parameters that we've talked about here are the key. Reynolds number, absolute importance for kinematic similitude. The flow patterns around the structure look identical at the same Reynolds number. And if you're looking at a closed pipe or an open pipe, then these would be the appropriate numbers to use. So you get some feel for these. And so you can use Buckingham Pi theorem to get these relationships, or you can also kind of guess them with some intuition, and they'll probably be something like this. So if you are doing things by Buckingham Pi, you should probably hope that your numbers come out typically to look like these typical relationships. Okay. What else? So there are a variety of these different non-dimensional numbers, very important because they govern the behaviors we're talking about. This is a table from your book. We've talked about the all-important one, by far the most important, is Reynolds number. Secondary are Froude number and Euler number for the reasons that we've talked about it. There are other numbers which we won't really use very much. Some of you, you'll recognize them. Cauchy number and the Mach number are the same. They're the ratios of inertia to compressibility. So this is inertia, you can see, right? This rho v squared term is just F equals ma, right? Rho v squared is the other way of writing mass times acceleration. And compressibility is just this stiffness of the liquid. It's not very important in liquids, but it is important in gases, air. And the other way of writing this, I suppose, if you remember, maybe you remember that our velocity, acoustic velocity, is equal to what? The modulus divided by the density square root. Maybe the second or third time we met, we talked about this number and how quickly your voice reaches my voice or my voice reaches you. I screwed up the calculation and worked out that the speed of sound was 10 meters a second. Actually, it's something like 300 meters a second. But because I think I used the density of water instead of air, I think. But anyway, so this is the velocity. So in other words, the acoustic velocity, you could write this also as v squared is equal to epsilon, the compressibility of the density. And if you substitute that in for this expression here, you get rid of the v squared. So in other words, is that right? Yeah, you end up with this. And so the Mach number, as you know, is just the speed that you're going relative to the speed of sound in air. So in other words, we'd call this number, if it's air, the speed of sound is c. And so if you're going at 600 miles an hour, 650 miles an hour, and the speed of sound is 650 miles an hour, then you're going at Mach 1. So commercial airliners go less than the speed of sound, and that's because if you go faster than the speed of sound, you physically can't dissipate all the energy that you're generating by pushing yourself through air, because the energy can only get away from you at the speed of sound. And if you're traveling faster than the speed of sound, all the energy, if you think about it, a plane is here, this is the nose of your plane. That's a pretty good plane, isn't it, with a wing on it. So you create sound here, it's trying to escape at some velocity c, but in the time that it's tried to escape from you, you've gone a distance here. So velocity is equal to length over time. So length is equal to speed of sound times time. So in other words, the distance this wave can get away from you is only this length in a given time. So as you travel to this point here, again, you're creating a disturbance that's trying to get away from you at some speed. So in other words, the location that this wavefront has traveled from you at this particular point is L, which is speed of sound times the time since you're at that point. At this point, it hasn't traveled anywhere from you. And so you end up with this Mach cone, which is where all the energy that the plane is trying to dissipate and trying to get away from you is trapped inside it. And so you have to build a very strong plane to be able to deal with that. And so if you're going faster than speed of sound at Mach 1, you need a stronger plane. And so there's no particular advantage for that for commercial airliners. And the attempts to do that, I guess, were the Concorde, which came online basically at the time of the oil embargo in the mid-1970s. And all of a sudden, with the price of fuel changing, it just wasn't a viable option. So, but we digress. Reynolds number, Froude number, Euler number, Mach number for compressible fluids, which we're not dealing with very much. Struhl number we won't deal with. Weber number is the ratio of inertial forces to surface tension, so capillary rise. Some of you, if you're involved in petroleum and natural gas, would see a number like this. It would be called a capillary number. And a capillary number is the ratio of not inertial forces to surface tension, but I think viscous forces to surface tension. And so if you're looking at the oil that gets trapped in the very small pore space, the capillary forces are very high. And so to be able to move that oil out of the pore space, you have to act against surface tension. You can use the capillary number, which has the diameter of the pore, the surface tension of the fluids between them, and also the viscosity, to be able to say whether you'd be able to effectively get fluid out of those very small pores. And so that's something we really won't deal with much more. Environmental systems engineers, the Peclet number is the ratio of advective fluxes to diffusive fluxes. They're not forces in this case, they're fluxes, but they're just ratios. Courant numbers are advective fluxes to the time taken. So it doesn't matter. It doesn't matter what they are. We won't read. So the important ones in this class are Reynolds number for kinematic similarity, and then for dynamic similitude, Froude number, and Euler number. Okay. Let's do a couple of examples. We have 2 weeks to talk about pipe flow, so let's finish this off and just introduce pipe flow today. Do a couple of examples. Having said that everything revolves around Reynolds number, of course I'll pick an example that really doesn't include Reynolds number so much. But the basic idea here is you have a structure that has some geometry to it, and you want to calculate the forces that you have to apply, or the forces that will be applied on this structure relative to the model. So what you have, viscous fluid flows past this, so you have fluid flowing past it. It presumably goes past it at some velocity, exerts some force on it that you have to act against to hold it in place. The plate has some dimensions, which are a height and a width. We're actually using a very viscous fluid, which is glycerin. So it's in pounds seconds per square foot. So it is more viscous than water, but we have a viscosity. We have a size for the model, 1 inch by 3 inches. So this is height is 1 inch, and this is equal to 3 inches in our model. And in our prototype, it is 4 inches by 12 inches. And so we'd like to do a model that's only 1 inch by 3, because it's much easier, and then run it as that, and then figure out exactly what this equivalent drag force would be. So we look at the parameters that describe our system. We have a velocity, we have a drag force, we have 2 length dimensions, and we presume that it could be viscosity. You notice in this case we're assuming that density has no influence. When we talk about external flows, we'll realize that you can get drag and lift. So lift is the force which is perpendicular to the flow direction. Drag is the force that's in the same direction as flow, as you can imagine. And they come from two sources. One, you could imagine if you have a very viscous fluid flowing past something, there's a big drag on it, and it's the viscosity that's causing that drag. The other way that you can create drag is by having a velocity coming in with a high density fluid that gets killed at this impact point, and therefore you get a pressure change at the stagnation point, which is what's pushing it downstream. So the two mechanisms by which you can get drag or lift on something, drag in this case, would be by viscous resistance or by killing a velocity, and the two properties by which they act would be pressure, killing velocity, or by viscous drag. So in this case, the assumption is that the flow velocities are small, and so the contribution by killing velocity is tiny in comparison to the viscous drag. It's treacle that's flowing around this thing. And so you don't know that, but that's the rationale of why we're ignoring this in this particular example. And so you have 5 parameters: a drag force, flow velocity, viscosity of the fluid, and 2 geometric parameters. If you go through the dimensions of these, force, length, I never use force, length, and time, I use mass, length, and time. But you see that force, length, and time are all represented. So the number of groups, number of pi groups, I think we used k minus n, right? K are the number of parameters, 1, 2, 3, 4, 5. Number of groups, force, length, and time are represented. So we know there are 2 groups. You don't know this, but with experience you would. If you see 2 simple parameters, the 2 length dimensions here are probably going to be one of the parameters. And so if that's the case, then you could combine the others in some way. You could do it using Buckingham pi, or you could do it by inspection, just by making sure that these things make sense. And in this particular case, you could show that the group that would come out of this would be force, a length. This could be either B or H, it doesn't matter. It would all come out in the wash. A velocity of flow and a viscosity. This for sure is dimensionless. I guess we should check whether this one is. What do we have? We have, if I use the units for this, a force is in newtons, a length is in meters, velocity is in meters per second, and the viscosity is in Pascal seconds. So Pascal is a Newton per meter squared, and it's Pascal seconds. So hopefully that works out. Meters squared, newtons, and seconds. So just by inspection. And so having said that, to look at dynamic similitude, we need to make Reynolds numbers the same. Here we don't really seem to have a Reynolds number per se, right? This is not a Reynolds number. Neither of these numbers, this is not an Euler number, neither of these numbers are Euler numbers, Froude numbers, or Reynolds numbers. So this is just slightly different. And it comes from the fact that we're dealing mainly with a viscous flow, and so it'll always actually look the same, irrespective of the Reynolds numbers, is actually the reality. It's for really low Reynolds number flows. And so what do we want to do? We want geometric similitude, so we want the model and the prototype. We've called this the prototype before, right? To have the same ratios, and not sure you use Bob's your uncle. You don't use that expression, I think, in this country. If you look at the ratio of these two, 1 to 3 and 4 to 12 is obviously the same ratio, so we satisfy that. And so then what we want, the other condition to be satisfied is, I suppose you could imagine that you could think of us drawing a diagram that looks like this, B over H, and if you like to think about things graphically, this is our other dimensionless number. And so if we do a test at one particular B over H, we end up with a point, and actually we know we're at that point, right? So this is the calculation for the model, but it's also the calculation for the prototype. So the basic outcome of this is that we know that d over diameter, drag force, length scale, velocity, and viscosity of the model has to equal the same for the prototype. That's basically what this figure says. We've done an experiment at this. We only have two pi groups, so it would have to look either like a point. Actually, yes, two pi groups, so it is a point. Forget the other thing I just drew. So in this space, if we have two pi groups, it's 1 point that we have only. We don't have a line. And so if we know this, we have this expression here, and all we do is we rearrange this expression to get the drag force on the prototype as a function of the forces and the dimensions and the properties, the velocities in the prototype, and we can solve for this, and so we can calculate for this. If, for instance, we thought that in looking at this behavior, that say the width of this might be important, then what we'd have would be another group here. And instead of being 5 minus 3, we'd be 6 minus 3, and we'd have 3 groups. The other group that we'd have would be something like width over height. I choose height because height's represented in this. And so in that case, we have 3 groups, this important one, this geometric one, and this geometric one. So this just means if we had a very thin plate versus a plate that was perhaps as large as h, in other words, it looked like a cube, then we'd expect to have different behaviors. If that was the case, then I suppose what we would have would be, we could have, okay, so in this particular case we have geometric similitude. So this would be a value for, say, width over h equal to 0.1. So we have a very thin plate and a tall plate, and we could do some experiments for the plates at different width to height ratios, and we'd get this graph. But now we have 3 properties. We have this dimensionless group represented, this dimensionless group represented, and this group represented. If the width to height ratio was only ever one value, then we'd only ever have this one line. And so for the cases where we have two-dimensional variables, if we're matching the parameter that we have in the 2 of these, then we really only need 1 point. If we're dealing with different width to height ratios, then we'd have a line like this. And so that's what our two-dimensional variables behavior would look like. If we had a number of these different width to height ratios, then you could imagine that we'd have a whole bunch of lines that might be for a width to height ratio of equal to 1, and 1 for equal to 10. And so that's the message from that, I guess, is the same as what we talked about on Friday, this idea. If you have 2 pi terms, then you'll have a curve that represents them. If you have 3 pi terms, then you'll have multiple curves that represent them. And so it starts getting a bit more complicated. But if you think about these things graphically in this way, then go on thinking about them that way, because that's really what we're attempting to do. Figuring out the least number of experiments. Okay? So, everyone okay? Hope I'm not confusing people. Yeah, just one more quick one. I guess we'll probably only get through this and a bit more today. So again, same kind of idea. Drag on a satellite dish. You know it's going to be 2 meters in reality, 80 kilometers an hour wind, and you want to do an experiment on a scaled down model, which is, I guess, a 5th scale, right? 0.4 meters instead of 2 meters. What airspeed do you do the model test is the question, and can you calculate the drag that's on this? So the drag would be this force, this squiggly D that we call it. And so our conditions. So our first condition is geometric. So does the field model look like the wind tunnel model? All the scales have to be the same. So if that's satisfied, then we satisfy geometric similitude. If we satisfy geometric similitude, do we satisfy kinematic similitude? In other words, Reynolds number of the model is equal, bless you, Reynolds number of the prototype. And so we've never really used it, but what is this? This is the kinematic viscosity, nu, is equal to the dynamic viscosity divided by the density. That's just a definition. We might have talked about that in passing on the second time or third time we met. So this is a velocity. This is a length dimension. I guess we could also write this if we substitute for this. This is just velocity of the model, length dimension of the model, and it would be viscosity and density of the fluid. So this is what our Reynolds number usually looks like. Velocity, density, characteristic length divided by viscosity. And if we use this different definition of viscosity divided by the density of the fluid, then we just look slightly different. And so the bottom line is that we want to choose a model velocity which satisfies this condition. This is the prototype, right? And so if we rearrange that, we get a model velocity. We know what the viscosity of the model is and the viscosity in the real one is. These two should equal 1, right, because it's air in both cases. We know that this scaling is 5 to 1, 2 meters versus 0.4 meters. And we know what the velocity of the real prototype is, which is 80 kilometers an hour. So we can calculate what the wind tunnel test is, and it's actually a pretty big number. Right? It scales with the only thing that's changing is the length scale, so it scales with the length scale, so it's 5 times the speed otherwise. And so if you then do the experiment at the same Reynolds number, then you can then guarantee kinematic similitude. No, sorry. What is it? Dynamic, right? Which is basically Euler number for the model equals the Euler number for the prototype. And that's what this is here. It looks a bit different from what we've seen before, but let me write it out. If you realize that the change in pressure, maybe acting on this, is equal to the drag force divided by the area. Too many D's in this, right? This is the curly D, drag force, divided by the diameter squared. This is diameter. This is our only characteristic dimension we have. So this is, yeah, I'm glad I drew them as a squiggly D. So this is the squiggly D, the force, and this is diameter. And so if you take Euler's number, which was delta P over rho density times velocity squared, and you substitute this number in, you get it equal to squiggly D, which is the drag force, divided by rho v squared times diameter squared. And that's what this number is here. You don't need the half on either side. Half just comes in as convention because it's a half v squared in Bernoulli, but you don't need the half. And so now the question is, you want to know what this is. What's the force applied on your pole as a result of the wind? You measure this in the wind tunnel. The densities of the fluids are the same, so you don't care about those. They'll cross out. You know that you're doing it at 2 different velocities, which we've just said, in the wind tunnel. And you know that the diameters of your model and your real conditions scaled. And so this is the expression. You know everything here on the right-hand side from your wind tunnel test. And that's it. That's all. And so this really is this much more standard way. The previous one we did was less standard, but this one's quite standard. Do we satisfy geometric similitude? Yes. Then our test must satisfy kinematic similitude, that the Reynolds numbers must be the same. And if that's the case, then we must satisfy, we can calculate the forces from this. And so if you wanted to draw this as a figure of what we've just done, this would be Reynolds number. This would be Euler number. We would do one experiment at one Reynolds number and get one value of Euler number. and then we do our, because the Reynolds numbers are the same for both the model and the prototype, then we know we're exactly at this point, and therefore the Euler number for the model has to equal the Euler number for the prototype. That's it. And so that's how fluid mechanics was done in the 1800s and is still done today, because even though we have these very fancy models and equations to look at things, then fluids are actually kind of unpredictable in their behavior. As you know, sometimes when you're happily flying along in a plane and all of a sudden you get jumped out of your seat by turbulence, it's very difficult to, in a deterministic way, to define turbulence. You have to define it in a kind of statistical way. And so even now, experimentation augmented by quite complex numerical models is really still the way by which fluid mechanics is done, and dimensional analysis is still that mechanism. Okay, right. So I think dimensional analysis is kind of a cool method to be able to do things. So we didn't quite get to this, but that's kind of okay. What is worthwhile doing? Let me set the stage for next time, and by just talking, maybe we've talked a little bit about open and closed pipe flows. And so just make the point of exactly how these systems are quite similar. And so it all revolves around this particular picture here. And that is that in these things that we've done so far, we've made this point that we satisfy geometric similitude, kinematic similitude, and dynamic similitude. What we'll find is when we start looking at pipe flows, and I've drawn this figure before, is that we've kind of been looking at, say, wing structures that look like this for external flows, or we've been looking at satellite antennae with external flows at some velocity. And of course, we could look at, imagine a closed pipe. We talked about this last time, and we could look at external flows around this at some velocity. And as a consequence of these, what we've been able to do is basically draw this figure. We can do the experiments at some Reynolds number. So a big Reynolds number means a high velocity. A low Reynolds number means a small velocity, given that the fluids are all equal. And so by doing experiments at particular Reynolds numbers, we've come up with relationships which have allowed us to say something about the forces that are applied on those structures. And so force on a plane, we're typically interested in lift mainly, but also drag, to calculate whether you could lift a certain weight off the ground. I suppose you're interested to make sure that here that the force applied on this dish is not so big that the moment snaps the pole. And this is really kind of like a wing, right? In some respects, it's just an external flow. And so in this case, you can imagine that if you're thinking not in terms of lift on this, I guess this is the better example, is if you look at the pressure that's applied on the front of here and the pressure that's applied on the back of here. I'm not trying to make this look like a funny face, but there's a change in pressure between back and front. You know, that's the reason that it would bend and snap. If you look at a pipe, then that would be the same thing. If this was closed here, you'd have a pressure here, and you'd have a pressure on the downstream side as well. And it's by virtue of the fact that you're killing velocity here, but also you're getting some viscous forces acting along this boundary, which are acting as frictional behavior. If you take the internal flow, which is what we're going to be interested in now, then now the velocity is quite obviously going to be through the pipe. You can imagine that you'd have these same viscous flows acting on the wall of this pipe. And you could also imagine that there would be a pressure drop between the upstream and the downstream. And so, philosophically, it's really not very different from this. You get a pressure drop that you're interested in here, and you want to know what the force is that's acting to be able to calculate if your pole gets snapped off. Here, you'd have the same pressure drop between upstream and downstream, but you'd be interested in knowing this to be able to figure out how much energy you have to supply in a pump, or how much gradient you have to supply in the pipes to be able to get fluid going along there that counteracts this. So what we'll do, and where we're going with this, is that we will develop a view of looking at this, and we'll develop some expressions that, as a function of Reynolds number, say something kind of like what the Euler number is, but it's actually almost the reciprocal of the Euler number. And it's going to be proportional to a head loss, and something that we'll call a friction factor. We'll call it squiggly F. In fact, you see the suggestion that that's going to be the case here. And we'll find that if we look at flows along pipes, we'll get a relationship that looks like this for laminar flows. But if we do our analysis in terms of all the properties that impact our system, we'll find out that things like the geometry of this, so the diameter and the length of this pipe, are two properties that come into this. So this will be a function of those properties, but also as a function of the roughness of the pipe. And that's something that we haven't talked about, but alludes to the idea that fluids are actually quite complex. And so what we're going to do next time, and don't pack your bags up yet because we'll look at a little video that kind of explains these points, is we'll first use dimensional analysis to figure out what the important groups are that describe our behavior. And we've kind of given at least the punchline away here. But we'll find out also that this group of the relative roughness of the pipe relative to its diameter, you know, the roughness on the wall, if you think about having a rough wall versus a smooth wall, also has a big influence on the behavior of pipes. And so we'll deal with that next time. So let's see if I have this movie here. So let's close up with this. So this is just looking at a plexiglass pipe, as you can see. Water's flowing along it. It's got a dye coming out of it right at this point here. And all that's happening is the velocity of the flow in the pipes being increased. So instead of being this nice laminar flow, all of a sudden as you get above some critical number, critical Reynolds number, then all of a sudden you get some kind of undulation in the flow. And still the mean flow is from left to right, but the local flow develops these little undulations and eddies that are in the system, which are actually an increased impediment to flow that you might want to avoid if you want to not use very much energy to push your way through the pipe. So I didn't, as you keep on increasing velocities, I'm not sure how far this goes, but as you get to much higher velocities, you'll get much more thorough mixing in the pipe, and you'll have to apply much more energy to be able to push stuff through the pipe. And, okay, give it 30 seconds. I'm not sure what happens. Yeah. So this behavior is actually quite difficult to characterize using theory, and so experiment is how you do it. You take these measurements in pipes, you measure the pressure you apply upstream, the pressure you get downstream, you measure the flow velocity that you get out of the system, and then you can make the chart that we will ultimately use, which are called Moody diagrams.